Hello and welcome to another episode of Oxford Online Maths Club. My name is James and it's just me here today and we're going to do some maths. Fantastic to have you with us if you're joining us live or if you're watching the YouTube catch-up thing. People are asking me admissions questions which I'm not going to do now in the live chat, but I might come back to them. I've tried last week to come back to questions at the end after I was live, just because it's easier for me to type answers when I'm not live. People are saying hello, which is nice. Hello everyone. And people are noting that we've switched over chat. If you're from before, then the chat is slightly different this term compared to last term. Sorry about that. We're all getting used to it. The clicking is me approving chat messages. Okay, good to have you all with us, especially if you've joined us following the open days. I know I did bang on about the open days quite a bit over the last couple of months, so I won't talk about the open days too much. Importantly, if you've been hearing all this chat about open days, but you don't live in the UK, then I imagine that's been quite annoying. The good news is that at the end of June, we're going to live stream some of our open day content out onto the internet live during the 29th of June open day. I don't have links for you, I don't have a schedule or places to go yet, but we've just made the decision that the 29th of June open day is going to involve some live streaming, I think. So that's a plan for people who didn't make it to the ones in April or won't make it to the ones in Oxford in June. People are asking about further reading. Because I've missed some further readings. There's about 6 episodes that are missing further reading. Essentially, I got really behind with the further reading, and those ones don't currently exist. I'm working backwards. So last week's got further reading. The week before has now got further reading. There are 6 weeks I haven't done yet that will at some point get further reading. This week I'm very pleased with myself because now the open days are over, I've caught up with last week and the week before, getting some further reading. My plan is that eventually everything will have further reading. There's about 6 weeks missing at the moment. James, your specs are spectaculous. This is how you get your message read out. James, your specs are spectaculous. This is serious and not funny. So like all the best. I couldn't even say it without laughing. Fermat's here as well, thank you. Big sad there from CRM, but open days. Okay, nice to have people with us. Feels a little bit more, I don't know, there's a lot of chat. I'm going to keep up with this. I can do this. This is fine. Right, okay. The pattern for this term so far is that we've been talking about classic problems, trying to solve them, and then trying to come up with variants on the classic problems, and things like that. So the way they've all gone so far is I've said the problem, lots of people in chat have sort of recognised it, knowing the answer already. But then eventually, hopefully, we get around to something that not everybody has seen before. If you haven't seen this before, then hey, you're one of the lucky people for who today is the first time you're seeing this. So I want to tell you about birthdays. So there's this famous problem that says something like, if you have 23 people in a room, so 23 people in a room, then there is a greater than 50% chance that 2 of them have the same birthday. My writing's quite small there, sorry, I'm going to get bigger again. Luckily the thing I've written really small is something that maybe you've heard before. Somebody says, happy birthday, James. It's not my birthday, but thanks anyway. Hi, he says, hi to Raphael as well. Did I shout out other people as well? I saw Harriet through there as well. Other people, just a quick shout out. I didn't shout out other people. Amelia, hi, I have Casey, Harriet, Alfie, hi CRM. How do I join the live? So somebody, you're in the live. Welcome to the live. Welcome to the live show. There we go. Good. Right. So this is quite a famous fact in some sense. There are more than 23 of us in chat right now, so this is probably true. This is going to be an awful thing to coordinate. I should have made a poll with 365 options in it, I suppose. We could test this theory if we had a poll, or if we had some way of working out if we can find 2 people who share the same birthday. Do I want to run that experiment? I think maybe I do. Oh, the birthday poll would be impossible. It would be too much voting. So this fact is supposed to be, it's sometimes presented as a paradox, I don't really know how I feel about presenting this as a paradox. I think quite have the confidence to try and put it off as a paradox. Um, because 50% is bigger than you might guess, or maybe 23 is smaller than you might guess for how long it takes. Everyone's saying their birthdays. Yeah, well, I mean, that counts as engagement, doesn't it, in chat? Well, let's find out if we can do this. August, okay, people have got other things here. October the 24th, brilliant, okay, this is going to work. While people are putting their birthdays in chat, which is good for my numbers, it's already happened, look, it's already happened. I think we're going to get a second match. Okay, I'm going to keep going through these. Everyone keep an eye on chat. I'm just pushing these through chat, sorry. In hindsight, there were too many people in chat for this to be even plausibly. I think we hit a match in there. I think we hit snap on Harriet, 13th of August, and like the very first thing was Dirichlet saying, oh, 13th of August. I think it's already happened, but we're going to keep going. In some sense, if there's too many people in chat, it becomes less surprising again, right? Let's all think about the pigeonhole principle very quickly. So the pigeonhole principle says if you've got lots of pigeons and not so many pigeonholes, then you have to have two pigeons in the same pigeonhole, just because you've got more pigeons than pigeonholes. I don't think chat's that popular. This live stream is sort of not large enough that that's the issue. But crikey, here we go. Somebody's offered me a burrito for my birthday. I haven't seen my birthday yet, so there we go. Cool. Is that another August 13th? What was the date we had before? We got three people on the same. We've got three people on August 13th. We've got Mihak and Dirichlet. There we go. Good. Okay. Good. When is my birthday? My birthday is the 28th of February. Thank you for asking. I don't think I've seen it 28th of February. Cool. Right. Okay. Good. Okay. So we've sort of demonstrated this with chat. Thank you for the chat engagement, everyone. There's a sort of calculation that people do to justify this. It works like this. Let's say maybe we want to think about having n people in the room, and then n will turn out to be, if n is 23, then this thing is slightly bigger than 50%. The calculation is not too hard. We can do it for n people. Okay, so let's put if n people are in the room. The best way to attack this problem is to think about the probability that this doesn't happen. Good. Oh, people are wishing me happy birthday. That's nice. Haha! And there's already a follow-up question in here. There's already a follow-up question about when do you have three birthdays in common, which we had in chat. We had three people on August the 13th. It's a slight problem with anonymous people that you end up with people, especially if you announce them publicly, that you can end up with, oh, that's weird, everybody's birthday is August the 13th. The sort of Spartacus effect where everybody volunteers to have the same birthday to make the maths work. Anyway, so this thing's easier to calculate. The probability that you all have different birthdays, then the thing that we want will be 1 minus this. Because if they don't all have different birthdays, then some of them are sharing a birthday. There's a subtlety there that if you've seen this problem before and you want to think about something else, then the question that's just been posted in chat has something slightly different. Yes, this is the problem. Think about this. There's maybe 2 pairs in common or 3. We'll get to that in a moment. Okay. So this probability that they all have different birthdays is... Best way to think about it is to imagine the people arriving at the birthday party one at a time. There's the birthday person there to start off with. Their birthday is today, I suppose, whatever it is. But then the second person who walks into the room, they need to have a different birthday to the first person, which there's a probability of, I guess, 364 out of 365-ish. So I think we're going to ignore leap years today. Now, as somebody born very near a leap year in a year that was a leap year, I'm very conscious of leap years, so that makes me slightly uncomfortable. But to make all the numbers simpler, we're going to ignore the tiny proportion of people who are born on leap years. Yes. Aha. I think we're talking about 365 day years. How much did it change? Not very much. Tiny. Only about, I guess, only about 1 in 1,000 people are born on a leap year. So the probability that anybody in the room is born on a leap year feels pretty small to me. Maybe about 2% or something. And then the probability that 2 of them do feels even smaller. This is on Harvard. This is on the Harvard MOOC. Do you want to put a link to the Harvard MOOC you've mentioned there? Yes. Okay. I suppose, considering that it's equally likely that people are born on each day of the year, which is not true. But in fact, the distribution being not equal only makes this fact more likely, I think. Anyway, this is nice. I've always found chat's very good at pointing out, when we're doing something applied or applicable, chat's very good at pointing out modelling assumptions. Assuming all days equally likely. Except leap years, which I've decided are impossible. Oh well, okay. So second person who walks into the room, there's this probability that they have a different birthday from the first person. Then the third person arrives at the party. They need to have a different birthday from both of the people already here. So that probability, there are 363 days left when they might have a birthday. And I need both of these things to happen in sequence, so I should multiply these probabilities. This is the probability that second person has a sort of different birthday. And this is the probability that the third person has a different birthday. Okay. Modelling assumptions. Oh, there's a formula in chat. Here, there we go. It's a little bit like, so it's a little bit like some stuff you might see at school with geometric distributions or binomial distributions. Anyway, you might have spotted a pattern already. This is going to keep going. The next person, well, it's getting a little bit less likely that they have a unique birthday compared to the people already in the room, because these numerators keep going down. So if I get to the nth person, there are n-1 days that should not be their birthday due to the n-1 people already at the party. So the probability that they have a new birthday that we haven't seen yet is 365 minus n-1. Okay. N probably does need to be smaller than or equal to 365 in order for this to make sense. Thank you. There is the link to a Harvard MOOC that includes this in the probability bit. Thank you. Oh, yeah, there we go. That's the Harvard MOOC : there we go. Good. Let's go with that one. Good. Okay. So there's some big calculation here for what's that probability. And I guess the punchline to the birthday paradox is, you work that out when n equals 23, you multiply them all together, and it works out as being about 50%. So it's about 50-50 when n equals 23. Which is fair enough, I suppose. That's one way to look at this. In chat, I saw people trying to simplify this, which I liked. Let's see if I can find that chat message. Yeah, something with factorials. I think it's not quite this with factorials, but I think we can do something with factorials. So I agree the bottom bit is 365 to the power of, I think, at the moment n-1, but you've got an extra 365 upstairs, but then maybe not quite that factorial. And now somebody's posted something with a p in it for permutations, which I'm going to have to think about, because I'm going to have to remember what p means in that expression. What have we missed? This is what we've done so far. There's this famous birthday fact that if you've got 23 people in a room, then more than 50% of them, there's a more than 50% chance that 2 of them have the same birthday. Let's put P for probability, bigger than 50%. And all we've done so far is try to work that probability out by thinking about the probability that it doesn't happen, which is a good trick in probability questions. Okay, good. So this is the probability that they all have different birthdays. Maybe the formula looks nicer if I put in this 365 over 365 over here at the front. Maybe that's nice. Well, I suppose that's equal to 1, so I'm allowed to write it there whether you like it or not, but maybe it makes it easier to simplify this down. Yeah, okay. So there's some stuff going on in chat as people try to generalize this into, into some sort of expression. I think we can use factorials to simplify this down a bit. So I think that this is, on the top, it's not quite 365 factorial on the top, because some of the numbers are missing. I think it's 365 factorial, but then it only goes down to 365 minus n minus 1. I've seen a trick for this before, that I can divide by 365 minus n factorial. So factorial means you start at this number and you multiply, working your way down. So 365 times 364 times 363 times all the way down to 1. If you want to stop after some of them, then you can divide by the factorial of the next number, because this thing in the denominator here contains 365 minus n, the next thing, the one that I don't want, 365 minus n minus 1, all the way down to 1, all this stuff that's sort of not in the numerator. I got less well explained as I went along. Yeah, so people try to subtract, but I think you want to divide. I like that one, but I think you want to divide to get rid of divide to get that. Yeah, so because these factorials are like lots of things multiplied together, you want to divide to get just these terms. Cool. Okay. Dirichlet's got some formula involving the 1 minus. And somebody wants to talk about house prices in London. Does n have to be bigger than 0? So I think our formula actually works. Oh my word, I've forgotten the thing on the bottom. That's a big factor on the bottom down here. Down on the bottom, I've forgotten this factor of 365 to the power of 365. My expression could not really have been more wrong. Whoops. Missing a 365. There we go. Yes. Or is it to the n? Whoops. Whoops. Still wrong. Still wrong, but getting less wrong. That's the mission, isn't it? Still wrong, getting less wrong? Yes, good. I have a little wobble thinking about the number of terms there. I think it's now the most recent thing in chat. Terry's got some capital pi notation. And as always, I'm impressed that people can type capital pi's into chat. This one hasn't quite convinced me because of the capital pi. Oh, yeah, okay, I sort of see what's going on. 0 up to y or something, different letters, but sure. Should it be n minus 1 or n? I would get really stressed about these. So because I introduced this term on the front, I think there are now n brackets. The brackets are numbered 365 minus 0, 365 minus 1, 365 minus 2, up to 365 minus n minus 1. So because this is 365 minus 0, there are n brackets. So the denominator is 365 to the power of n. Whew. And on top, I think I've got everything else right. Yeah, people are still sad about Slido. We swapped. This one lets me do maths in polls, which yeah, it's a bit difficult in Slido. And it makes us all be anonymous. And I can do host messages. A bit complicated. Okay. Also, it's the university supported one, so I get different sorts of support for this using this version of chat. Okay. I was quite excited when I saw this formula because I thought I could just plug it into my computer and do some calculations. My computer's not very happy with this. When I tried to give this to my computer to do some sums with, it informed me that 365 factorial is infinity, so can't work this sum out for any value of n. It just complained at me a lot because it thinks that 365 is unimaginably big. It hadn't even got around to looking at the denominator, which is also, I think, unimaginably big for my computer. This is a little bit disappointing, and it meant that actually I I got my computer to work out this product rather than simplifying it. I got my computer to work out this product. It's about 0.5. Yeah, Slido has replies. I haven't worked out if VBox has replies or not. I did like replies. Apparently Wolfram Alpha does this just fine to work out that number when n is 23. That shows me. I put this in my computer in a stupid way and got my computer to do something stupid. Anyway, this turns out to be when n is 23. This is about 0.5, which is nice. So questions in chat. What if a year only had 100 days? I think something nice about doing the algebra with 365 is that 365 almost works like a algebraic variable in this. You can really see where the 365s are. So if you want to switch out 365 for a different length of year, like 100 days, then it's kind of clear where you put that in the final answer or throughout the working. You get different answers. Yeah, so 360 factorial is too big for my computer, but somebody in chat has told me how big it is, possibly with the help of Wolfram Alpha, who knows. Yeah, I was doing something very silly with MATLAB, but I regret it now. Okay, everyone in chat who knows about computers is telling me that their computer can handle this expression just fine, produce lovely plots, I'm sure. Good. We're running this on PC. Thanks for asking. Yeah, so this question: Do you want to make 365? Do you want to make n less than or equal to 365? You probably do. Probably do. Otherwise, this starts to get a bit scary, doesn't it? Yeah, let's put a thing in here. Let's say that we want. What do we want? Something like. Let's put some safety valve in. Seems like a safety valve. Thank you. Good sort of safety valve bit in there. Different calculation though. Ooh, is that plot? Hang on. Let's see that. Oh my word, Wolfram Mathematica can just do this? Oh. Thanks, Dirichlet. Oh, look, people are just showing off now. That's a this is like a team group project thing. Can n be 0? Yeah, I thought about that in my head while I was writing on the board. I don't know what this means if n equals 0. I'm not sure I believe in my formula, whatever it says. I think it says 1, which would correspond to there being no probability. This is the probability they all have different birthdays, which would correspond to the probability, yeah. This would be 1, which would mean there are no probabilities that two people share a birthday if you have no people in the room, which is not a great fact, but hey. Negative factorials, let's just not do them now. If you have 366 people, then it's impossible for them all to have different birthdays in my system up here. By the pigeonhole principle, too many people. Good. That comment just says the words OOMC. Yeah, there we go. If n equals 0, then this probability is, oh no. I think if n equals 1, I would hope that yeah, let's check n equals 1. So if n equals 1, this on the bottom is 365 times 364 factorial, which is 365 factorial, which cancels, which is 1. So this says that if you have one person in the room, there is no probability that two of them have the same birthday. Brilliant. top maths facts. Yes, the probability of all 365 people having different birthdays is, I think, what you get if you continue this pattern. And you keep going all the way through to n equals 365, which is then 365 factorial divided by 365 to the 365. Good question, Jack. One that I could, turns out, answer with my big formula. N equals 365. People are talking about negative factorials now. They can be defined using something called the gamma function, says Dirichlet. That's just the words, OOMC. Yeah, okay, they're not words, they're letters. Thank you, chat. Good, okay. And people are maybe going to do some binomial distributional stuff. So I had a different calculation. Let's put this paradox thing on the board so it's there in a different colour, just for fun. Turns out that n equals 23 implies this is about 0.5. There's a calculation due to a mathematician from the last century that lets you work out kind of where the 23 comes from without doing loads of multiplication. So I thought I'd show you that calculation. I don't know how long this is going to take, so we'll see how this goes. Yeah, how do we simplify this? So I simplified it at the bottom using some factorials, but I'd like to show you a different thing. Oh wow, with 365 people, the probability they all have different birthdays is 1.4 times 10 to the minus 157. Sort of incredibly unlikely. And then after that, I guess that it's just 0. If there are 0 people in the room, here we go, this is the philosophical statement. If there are 0 people in a room, the probability that they all have the same birthday is 1. The probability that 2 have the same birthday is 0. That sounds very true, unfortunately. Makes me uncomfortable. Oh, somebody here got an Oxford interview and got asked this question. Fun. Okay. So here's an argument to make this bit in purple. This sort of turns out you do some calculations. I can tell that some people in chat really like computers and really like doing this sort of calculation. There's a calculation from a mathematician called Paul Halmos from last century that just does this a little bit faster. So it works like this. Let's take these brackets. And we're going to write them in a very particular way. I'm going to write them out like this. Maybe this would have been a good way to write them to start off with, that this first one's 1, the controversial 1 at the front. This one is a little bit less than 1, and then the next one is a little bit less than 1, and the next one down is a little bit less than 1 as well. And this last one here is 1 minus n minus 1 over 365. Maybe this makes it clearer that there are n brackets as well, by the way, including that 1. Okay, so our challenge is we've got a 1 multiplied by a lot of brackets. Each of them are a little bit less than 1. So multiplying these out would be really horrible because by expanding these brackets would be a real pain. Something that's easier to multiply together is exponentials. So there's this idea that we can take the fact that, how am I going to write this? So this is I think all we're going to need. Here's a true fact. Okay, so first I have to convince you that this fact is true. I think I've got it the right way around. Let's check I've got it the right way around first. So here's my exponential like this. This is my e to the minus x. And this is my sort of sanity check. And then this line is going to be 1 minus x. Oh, it should be a straight line. Oh. Does this have a straight line tool? Let's find out. Shape, sticky notes, text. Ugh, loads of stuff. Straight line. Amazing. Right, cool, good. Drawing a straight line. Yes, there is an expected number version of this question as well. Okay, so proof of this, I need a greater than or equals to 2 sign here because I've included 0 for no real reason, but hey. Proof of this, when x is equal to 0, both of these expressions are 1, these graphs both go through 1, and then after that, between 0 and 1, and I guess also forever, but in particular between 0 and 1, e to the minus x has a greater derivative than 1 minus x. How do I prove that? Well, so check the derivatives. The derivative of the pink line is minus e to the minus x, and the derivative of the purple line has derivative minus 1. But over here, e to the minus x is less than 1 because this exponential is decaying, so this is bigger than minus 1. So it's decreasing, but it's not decreasing as much. Yeah, thanks. Bigger than or equal to because I included 0. Don't really know why I included 0, not really sure I needed that. Press L for line, thanks. Slightly too late for me, but yeah, cool. Okay, good. There probably is a mean value theorem. Let's not go into mean value theorem. It's true because I've drawn a picture and I've checked the derivatives. Okay, this is quite a good fact. E to the minus x is bigger than or equal to 1 minus x. If you know the Taylor series for exponentials, then you can write down some more terms and you can play games where you work out other approximations for exponentials, but they're not relevant right now because the things I've got in the brackets all look like 1 minus x. So the big idea is that we can bound this probability. This is the probability they all have different birthdays, which maybe is what I expected, but actually it's small. It's smaller than, I'm going to forget about that one for now, e to the minus 1 over 365, and then this bracket here, this is small as well. This is smaller than e to the minus 2 over 365. This one is smaller than e to the minus 3 over 365, and so on, e to the minus n minus 1 over 365. All of these terms are sort of small, so this is the idea that we can replace all of them by writing out this big inequality to replace them all with exponentials. Exponentials multiply in a nice way. The rule for multiplying exponentials together is that you add the powers together. And if I add the powers together, then I get, well, everything's over 365 up there in the power. But I'll get a minus 1, a minus 2, a minus 3, a minus 4, all added together. You add the powers together when you combine exponentials like this. That's the triangle numbers. That's an arithmetic regression with first time 1 and common difference 1. Better known as the triangle inequality, better known as the triangle numbers. So this product I've got over here is easy. It's this. So some messing around with exponentials and messing around with summing a series to get e to the minus n minus 1 over 730. So all we need to do to find the value of n for which this paradoxical fact is true, that this is smaller than 50%, if we can find a value of n where this is less than 50%, then we're done. We've bounded the probability by 50%. So we want to know when is this, so this is roughly equal to, so we've got some exponential stuff. Yeah, exponential stuff to work out when this is equal to or less than 1/2. So this is less than 1/2 if this is big, if this is bigger than logarithm base e of 2. Yeah, there's going to be some multiplying out, there's going to be some logarithms going on as well. There is it is a geometric progression actually. So the 730 comes because upstairs, I've got upstairs in the exponents, I've got, forget about the minus sign for a moment, I've got 1 plus 2 plus 3 plus 4 plus dot 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 plus n minus 1. That sum is equal to n minus 1 over 2, triangle numbers or something. So that's giving me an extra factor of 2. 2 times 365 is 730, I think. Good, okay. So this gives you a much simpler rule about when does this happen. So it turns out that this happens, and you can use quadratic equations or something on that if you work out how big 730 log 2 is. I guess downside you need to work out. Shall I slow this down? Shall I slow this calculation down? I think I may have done that calculation too fast. Yeah, let's do this a little bit slower. Okay, so hopefully I've got away with this exponential where I'm just combining together the powers, adding together the powers. This thing here, let's do some more steps in sort of here. So e to the minus n minus 1 over 730 is less than 1/2 if minus n minus 1 over 730 is less than ln 1/2, doing ln of both sides. Ln is an increasing function, so this is okay. Which happens if n minus 1 over 730 is bigger than negative ln 1/2. But there's this rule for logarithms that's equal to log 2, like that. Discord is unofficial and not endorsed by Oxford. We're not responsible for anything that happens if you click on external links. Yes, here we go. Okay, good. And then that turns out to happen if n is 23. It's much easier to check numbers in this. If you want to check numbers, it's easier to check numbers in this than it is to check numbers in the original expression. Mostly I'm saying check numbers because I'm too lazy to go and solve the quadratic equation. And even once I've solved the quadratic equation, I'll need to think about how big log 2 is. I suppose I could use a bound on log 2. If I don't want to work with log 2 and I want to work with some fractions instead, I could go and just try values for n, and it turns out if you plug in 23 into this, then you get something that's bigger than log 2. You can do this more pencil and paper if you prefer pencil and paper, rather than using your calculator for log 2. If you use the fact that log 2 is less than 17 over 24, that just about helps, I think. If you want to, if you want to formally get all the way down to 23 with pencil and paper, then I think you're going to need the fact that log 2 is less than 17 over 24. How do I know that log 2 is less than 17 over 24? Glad you asked. That's a math question that we set last year. So it's a math question 2021, question 2, gets you to prove that log 2 is less than 17 over 24, which is, I thought, quite a fun question. Okay, madness. I quite like this sum. It is just a bound. There's an inequality in there, so what we're proving is that 23 is enough for the probability to get below 50%, that they all have different birthdays. It is just a bound, so it might be the case that 23 is sufficient but not necessary. In fact, this approximation is in fact really good, especially for smallish values of n. If n is for the range where the probability turns out to be between roughly 0.5, the approximation is pretty good. It's really good for small values of n, and it stays quite good for larger values of n up to about 20, which is maybe surprising. An exercise to go and try might be, can you sketch this graph, e to the minus n, or maybe with an x instead of an n, I suppose, e to the minus n minus 1 over 730. That's not a great question, is it? Maybe a more pretty version of this question might be to sketch you see, if I tell you to do this though, then everyone will just go and put it in Desmos or something. I don't even care about the over 2 really. Okay, here's the kind of homework. Go and give that one a go. I think I like that. Yeah, cool, good. Bye, Ali. Hey, someone likes that. Yeah, someone's calling me out for saying lun instead of log. Did I mean log? I say log. Look, I'm trying really hard to write lun and say lun because I think that's what people want me to do, and it's sometimes I say log when I've written lun, because for me that's the only one. That's the only one I use. Something about Gaussian integrals maybe, or something like that. So this argument, to rewind a little bit here, I really like this, replacing the brackets with exponentials so that we can do maths on them with pencil and paper. That argument is due to Paul Halmos. Paul Halmos is, I think, Hungarian mathematician. Other things attributed to Paul Halmos are the word if and only if being shortened down to IFF, if with 2 Fs, to mean if and only if. That's something that Paul Halmos claims is Paul Halmos's idea. And also the idea of writing a square at the end of your proof to indicate that you finished, instead of writing QED. That's also accredited to Paul Halmos. Oh, someone in chat says LN. Someone in chat says if. Perfect, right, okay. Everyone's put it into decimals already. LN, wow. Okay, I really like this calculation. I think it's nice. So in particular, if your number of days in the year is different, then a good heuristic approximation from sort of this expression up here, if you've got D days and you've got N people, then the prob all different. The approximation e to the minus n squared over 2d is pretty good, which gives you a nice quick way to work out that probability. People love Desmos. I'm really trying to get better at Desmos. Have a writing the square if we can tick it afterwards. Right? Come back when marking, just come through, tick the little proof square. This exponential, I suppose, contains the paradox that it decays really quickly with n, that when n gets up to 23 for the original problem, this is really small. This also features in, was that not the real link? It looks all right to me, or maybe not. Who knows? Always watching out. This features in something called a birthday attack, which I promise I'm not trying to be topical. Birthday attack is when you've got something that in cryptography or something, you've got some sort of hash function that tries to take something and verify it's authentic by calculating, based on your object, calculating a number. It's a very difficult function to undo, so it'll be very hard to, if you change the object, number's different, and it's hard to change the object in a way that ends up with the same answer. But there's this thing called a birthday attack, where if you can create lots of objects that are pretty similar, and use the hash function on all of them to make their numbers, then it's not that hard to find two that are slightly different, maybe two different objects that have the same hash, the same, what should be a random output from this function. It's not too hard to find two different things that have the same birthday, have the same output, and then you can use that for slightly nefarious things. If you can find these things that are actually different but have the same hash, that's something called a birthday attack. Why is it n squared and not n minus 1? I was too lazy. And if n is bigger than 1, then n and n minus 1 are about the same size. It was laziness, really. I'm imagining d being quite large, I think, so I can get away with that. But you're right to call me out for that. What is a hash function? So a hash function might be, all you really need is a function that takes an input and returns an output in a way that's deterministic but hard to invert. The idea is, the idea is that you've got you're trying to prove. It's really hard to dance around this topic without sounding like I'm talking about NFTs. I promise you, I'm not talking about NFTs. You're trying to sort of sign a thing to prove that it's not being tampered with, and I'm not sure I'm really teaching you how to hack. People are really unhappy about that n squared minus n thing. If I had large n, for biggish n squared minus n and n squared are about the same. I can get away with that, just about, I think. Shouty opinions on NFTs, which we're not doing NFTs. Should we double it to make it positive? Double what? Sorry, double what to make what positive? That's a scary message. Probably means I've missed a factor of 2. I am not responsible for any missing factors of 2 today. Okay, so we had an original problem. We looked at some way to write down the probability, and you can go and put this into a computer. Apparently Desmos can handle this. Wolfram Alpha can handle this and do some sort of nice plots. It's actually quite fun to think about as well. If you know how to get random numbers out of a computer, if there's such a thing as random numbers, then if there's such a thing as random numbers at all, then you can play games where you try and simulate this, where you imagine that you're having a simulated birthday party with 23 people, and you give them all dates of birth, and you see, are there 2 people with the same birthday? I wrote that code up this afternoon just to check that everything was going okay, and it was, I don't know, surprisingly fun to write up the code, because then when you're writing up the code, you can think of other variants of the problem. And earlier on, people suggested some. We're not doing NFTs. Yeah, so a good idea would be, thanks for mentioning passwords though. Oh, people are telling me about hash functions in chat. They can tell that they could tell I was struggling. Good. That's a really good application, by the way. So yeah, websites can store, instead of storing your password, they can store a function of your password. And then when you type in your password, they apply the function and check that those match. And then they're not technically storing your function. Good. Okay. So we had this calculation. You put this in a computer. You could try doing some simulation if you get your computer to invent random dates of birth. You play with different numbers. Somebody earlier asked what happens if, what's the probability that you get 3 people with the same birthday? That question's much harder. It's much harder because there are more things to rule out. In this original version of the problem, it really relies, the argument that we did really relies on either they all have different birthdays, something we can get hold of, or at least 2 of them have the same birthday. If you want to start talking about 2 pairs or 3 people having the same birthday, then it's much more complicated because there's lots of things included there that you'd like to rule out. In particular, if you're looking for 3 people with the same birthday, to do the calculation theoretically, one way in would be to think about the probability that they all have different birthdays, and then to think about the probability that exactly 2 of them have the same birthday and the others all have different birthdays, which is hard to think about because there's lots of different combinations and possibilities for how that might happen. Good. If this was an interview question, can we ask the person who had this as an interview question, do you want to share what happens during your interview question? How much of this do we get? I sort of think this calculation, where you compare it to exponentials and do some multiplication, I sort of think that might have been quite a fun interview question. I can't do it now because it's on the live stream. It might have been a fun math question, except can't do it as a math question because then everyone will complain that there's too much probability in the math question. This is probably too much probability for a math question. Yeah, so the variant that Dirichlet mentioned to have the expected number, which is subtly different from the probability that there are any, because of the possibility that you can have 2. There are some asymptotics for that one that I can't remember off the top of my head. Asymptotics like these approximate heuristics that I'm not quite getting away with. Does Oxford ever repeat interview questions? I've never repeated interview questions between years. I can't speak for all my colleagues. I think it'd be quite a bad idea. But maybe if they think that none of the people have seen the question before. What's the probability of having 2 birth dates match in a group? So 2 birth dates instead of exact birthdays, having day in history. So now we're allowing for people the fact that people are born in different years. That introduces a lot more days, so that probably brings the probability down a bit. Maybe the punchline is that, hey, if you make the number of days 50 times as big, this probability goes way down. You need to make n. Yeah, okay, so if you make the number of days 50 times as big by thinking about the number of different days across maybe 50 years, then you only need to make n squared 50 times as big, so you need to make n about 7 times as big. So I guess you need about 150 people. I think that's what I'm saying. I think if you've got about 150 people, test of my heuristic, I think that maybe if you've got about 150 people, there's about a 50% chance that 2 of them were born on the same day. Not allowing for the fact that distributions non-uniform distribution of birth dates. Okay, we've had that one before. Good. That's a link to a video. We're gonna see what happens if people go for that. Only tutors in colleges interviewed people. Yeah, I'm a tutor in a college. And also sometimes people, interviewers might be tutors, or they might be DPhil students who've had training to do interviews alongside other people. Some interviewers have observers as well. Usually tutors, but not always. Graph sketching questions, homework is actually not too hard. Oh, I'm glad I gave you some homework that's not too bad. Trying to work out what I'm doing next. where are we pivoting to for this? We've mentioned attacks. We've mentioned three. No, so 3 people having the same birthday was a complicated question. Something that's easier to work out with computers, I think, because I'm very lazy at writing computer code, is looking at the number of distinct birthdays. And I wonder whether that might be an easier question to ask. So number of distinct birthdays, that kind of merges together the question about having 2 pairs, merged together with the question about 3 people having the same birthday. But counting how many different dates of birth you have in a random sample is a little bit easier than trying to count how many pairs and threes you have going on in there. Other extensions I thought you might be interested to think about are sort of playing cards, where sometimes people are interested in the probability that you draw some cards and you have some matches. Maybe you have 2 sevens or something like that. You have a pair or 2 pairs. Talking about 2 pairs and 3 of a kind made me think about drawing cards of hands of cards. Here the probabilities are slightly different because when you draw cards from a deck, they're not independent. You draw a card and then that tells you more about the cards that remain in the deck. So that's different. Again, I can think of ways to try and simulate that in a computer with some randomness. But probably doing the probability calculation feels quite hard. Especially, what's your question? Like, what's the probability that you have? What's the probability that you have two kings or something? Yeah. Okay. So let's make this into a question on the board. Let's say you draw 5 cards. Probability you get a pair. I think this is hard. I'm not expecting that one to have like a nice calculation. Yeah. I am currently teaching for New College, thank you for asking, and I have previously done interviews for Christchurch, which was one of those. 2 days. There's a person asking about citizenship a lot, which I don't really get. I don't really understand how that makes it. Do you want to put different citizenships into the different possibilities, which makes D larger? Good. Oh yeah, how many cards? I think I've got 52 cards. 52 cards, and there are 4 of each. What are they called? 4 of each. 4 of each value. There are 13 values. This feels hard. It feels like. So I'm not really sure about this question because it feels like you put it into a computer, you simulate it a lot, the probability comes out, and there's the probability. This is probably relevant for poker, depending on what sort of poker you're playing, who knows. Goodness, we're not doing NFTs and we're not doing poker. Are they called suits? I think the suits are the other way. I think the Dickens also said suits. Are they called suits? I meant 4 of each. Anyway, never mind. This question is probably you put it into a computer and you work it out and you get a number back. Who knows? Maybe there's something interesting you can do there with probabilities. Maybe. Maybe not with these numbers. Maybe there's something nice you can do there. I wanted to present you a kind of heuristic that doesn't work. So this one's really good. This Paul Halmos calculation for finding these exponentials is amazing. Here's a heuristic that doesn't work, and it might be instructive if you want to think about these problems more. It might be instructive to think about why this doesn't work. Okay, so here's an argument that doesn't work. So the probability that there are 22 days represented in 23 people's birthdays. Oops. So this would be the probability that there's a clash, that you look at the 23 people's birthdays and you only get reported back 22 different days. Well, that should be 365 choose 22 for what are those 22 days that get reported back, which days are the birthdays on. You make a list of everybody's birthdays, and 23 people, but I've only got 22 names on 22 dates on the list. So 22 choices of what those 365 choose 22 choices of what those dates are, and then everybody's got to actually have birthdays in that list. So this probability is the probability that that each of them has a birthday. Each of the 23 people has a birthday in that 22 out of 365. This doesn't work because this number turns out to be about 9 million, which is not a sensible probability. Probability is usually between 0 and 1. This number's about 9 million, I think. So this has not worked at all. And maybe a fun thing to think about would be, why does this argument, which on the surface almost seems logical, I think, almost seems like it makes sense, why does this not work at all? Okay. I don't know what that means. Hang on, I think I'm learning French. Somebody in the chat's teaching me French. Give me a moment. I have no idea what's going on in chat. Right, okay, it's just... Okay, we're not doing that one. Cool, good. Something like binomial distributions. Yeah, it felt a bit binomial, didn't it, at the start? There was a bit in there that felt a bit binomial, but then maybe less binomial over time. Something that's weird about this distribution for the probability that they all have different birthdays is that after a while it's just 0. That there's some probability, if you have 23 people, some probability that they will have different birthdays, but then after a while this sort of tails off, and then after 365, as soon as you've got 366 people in the room, the probability is 0. There's no probability that they will have different birthdays. So it's sort of an interesting distribution. This sum all the way up here, this thing we calculated. It's sort of an interesting distribution. It decays and then it drops down to exactly 0 after a bit. I guess it's only defined on whole numbers, so it doesn't really make sense to talk about it jumping around between values and 0. But yeah, I think that was interesting. Yeah, so that argument at the bottom didn't work at all, but I like to show you stuff that doesn't always make sense. Cool, right, okay. I think I've run out of content on this extension problem, unless anybody in chat has got suggestions about other ways we could extend this problem. Yeah, multiply it by probability of failure. So what's my probability of failure here? So it feels a bit binomial, right? I want them all to... I see what the binomial thing is now. This feels a bit binomial, I suppose. I mean, it's wrong. It's just completely wrong. So let's not think about it too much. There we go. Any other suggestions for how we could adapt to this problem? We've got about 2 minutes before wrap up at 6 o'clock, I think. This has never happened for me to run out of things to say, but goodness me, I've even shown you a thing that doesn't work. I suppose the natural conclusion to all of this is the calculation that's also not hard, which is what's the probability that all of the people have the same birthday? That's the sort of natural end point of this, right? And that one's easy to calculate. So somehow it's the in-between problems that are hard to work out, the probability of having 3 on the same day or something like that. Okay, I think I'm going to wrap up in a second. Ooh, somebody's made a video, somebody in chat's made a video, it's possibly, hang on a minute. Oh no, okay, that is a video of some stuff going on Huffman codes, which we mentioned in the further reading last time. Cool, okay. It's my favourite bit of pure maths. I'm trying to get into Galois theory at the moment. I'm trying to get into it. Really want to understand Galois theory. I think Galois theory might be really good. If I ever work out Galois theory, then you will find out about it on the live stream. We will eventually do some Galois theory. It's the branch of maths that proves that there's no tidy formula for solving quintic equations, degree 5 polynomials. There's no nice formula involving normal operations and radicals to write down the roots in general for quintic polynomials. We've got a quadratic formula. There exists a cubic formula. There's a quartic thing out there, but there's no formula for quintic polynomials. But it's also the branch of maths that tells you facts about geometry, about which shapes you can construct with a straight edge and compass, and it tells you lots of other stuff as well. It's all applicable in lots of different directions. So that's something I would like to have. Somebody asked about the probability that it hits 99%, which I didn't work out. Maybe I could have gone back into the calculation. The heuristic stops being very good. This heuristic stops being very good when you get close to 1. I suppose because the brackets that you're multiplying together get further away from 1, so the approximation around here, close to 1, is less good. So the things you're multiplying, it gets less good on the way through. So I'm not sure I can use my heuristic to calculate the 99% point. But people with computers, people who are happy to get their computers to multiply things together, can have a go at that. It does involve Galois theory does involve group theory, which we've talked about on the stream a couple of times before. An even smaller probability for them having different birthdays, and also it's the days of the year. Derivative of acceleration is called jerk. Sometimes, or is it? Yes. And then the next ones are called snap, crackle, and pop, I think. Book recommendations in the prospectus. If you search for Oxford Maths Department prospectus, we've got a departmental prospectus, which has got some book recommendations you might like, which you'd have a look at. You're not expected to read all of them, or any of them, or most of them, or some of them. I've read a couple of them. But if you want to see a list of books, then there are some in our departmental prospectus over there. And Richelais explaining Galois theory to me. Ooh, yeah, goodness. Some of those words mean something to me. Goodness knows. Right, okay. I'm rambling. I can tell when I start rambling. Thank you very much for watching. Sorry, it's a bit of a strange one. Still feeling the open days, I think. I will see you next week for another episode of the Oxford Online Maths Clubs. Oh, Maths Clubs, plural? We're doing that take again. See you next week for another episode of the Oxford Online Maths Club. Bye.